Hello. In this video, I'll be introducing electrical concepts. These are necessary to understanding the basics behind electronics, especially hobby electronics that we'll be covering in future videos. I'll be covering some of the history of electricity, what is electric versus electronic, which is different, the difference between analog and digital, and the importance of Ohm's law. I'll also be briefly mentioning circuit simulators, which you can try out some of the concepts from this video in a virtual environment. So, you've probably heard the term electricity. Some of you even know it derives from the term electron. Now, nowadays, when we think about an electron, it's one of the particles inside of an atom. But historically, it had a much different definition. It actually stems from one of the Greek words for amber, um, known as electro, which actually came from the fact that ancient Greeks would notice that those particles would be attracted to and cling to their amber jewelry. The cause of this effect was really unknown for the better part of 1500 years. And at times it was actually considered aspects of the human body, which was natural considering this was jewelry they were wearing. And some people believed it was linked to the balance of the four humors in the body. This is a medical theory that was later discredited. Um, However, the real serious study of electricity began in the 18th century, although we did see bits and pieces in the Middle Ages, the Renaissance, and there may have been even ancient use of electricity is evident in the Baghdad batteries, but how that was used and what that meant is incredibly uncertain. Going back to the 18th century, most Americans, such as myself, are familiar with the stories of Benjamin Franklin being a scientist. Most famous story is about him flying a kite during a thunderstorm. Although most people, when they tell the story, they leave out certain particular details. The first detail is that attached to the kite was a metal key, and attached to that key was a long copper wire that led from the key to the ground. This was a basic demonstration of electricity, and more importantly, how it could flow from one point to another. This concept later uh, involved Benjamin Franklin inventing the lightning rod, so that's like the lightning bolt would hit a metal point that was just slightly taller than the structure it was on top, and it would flow through a copper wire safely to the ground. Um, Now, the actual facts of this story aren't important, but this gives you an idea of how study happened in the 18th century with electricity. It was more of a concept demonstration than any practical. Although, again, obviously, in the case of the lightning rod, it was very practical. The 1740s, a couple of decades prior to Benjamin Franklin's experimentation, there was a thing called Leighton jars. They were actually invented independently by a couple of people around the city of Leighton in the Netherlands. Basically, what they did was they could store static electricity, and they were essentially precursor to batteries and capacitors. Since this was just working off static electricity, you could demonstrate storage of electricity, but you couldn't do anything practical. By the time of Benjamin Franklin, these were well known, and he most likely constructed some or of a similar design. However, in 1800, an Italian scientist, Alessandro Volta, basically invented the first modern battery or chemical battery. At times, it was called the Voltaic pile, and basically, it sandwiched layers of zinc, copper, and salt water. Although later they used acid-soaked cloth, which most importantly created a continuous electrical flow as opposed to the static electricity that was with the Leighton jars. This provided that basically electricity could be generated chemically, and that's an important concept of how batteries work. Now, this all these experiments show that electricity could be both converted from and to other sources, light, motion, heat, chemicals, etc. Keep in mind that electricity also dissipates as heat, and that's why we often see cooling solutions, even if we can't see them personally, for everything from transformers to computers to whatever. And excess heat can actually interfere with circuit operation, damage, or destroy components. Although there's some cases where that heat's good. If you've ever used a toaster, it's metal coils where electricity flows through them and generates heat. So the question is, what is electricity? How does it work? what is electrical flow and what happens to create it. Now, as you probably know from any basic science class, everything is comprised of atoms, which have even smaller particles in them: electrons, protons, and neutrons. Electricity is basically what happens when there's movement of electrons between atoms. A conductor is basically any material that allows for electrons to flow easily between atoms, and an insulator does the opposite. Now, actual electrical fields are basically produced between the interaction between electrons and protons, and they exert a force on other charged particles, which results in the actual movement. When an electron itself enters an electric field, it's pushed in the opposite direction of the field, which basically creates a fairly steady stream of electrons. Now, keep in mind that electricity and magnetism are actually two sides of the same force, the electromagnetic force. Magnetic fields are also produced by this movement of charged particles, which forces the electrons into a very specific pathway perpendicular to the magnetic field. Now, this gives us our definition of electricity, which describes both the presence and the flow of electrical charge through interactions with these electromagnetic fields. Sometimes electricity is described very incorrectly as water flowing through a pipe. However, this is actually not how electricity works. Electrons actually flow through the generated electromagnetic fields, not inside the conductors themselves. This is a very important point. The result of this is we can actually detect the EM fields without tapping into the conductors. And if it was water flowing through the pipes, this would not be possible. Um, EM detection is used by hobbyists, professionals, and even the occasional ghost hunter. Now, an electronic device is basically any electrical device that can process and manipulate electrical signals, tasks such as computation or intelligent conversion. The actual origins of the term electronic are a bit murky. It probably came about in the early 20th century, but by the 1930s, it was a very actively used term used by scientists to describe any kind of machine that used electrical components to process signals, such as that was used in computation. An electronic device can basically be described as either analog or digital, and in many cases, they can be both in a lot of ways. Um, and a lot of times, analog devices have been replaced by digital ones. You'll see both types just working side by side. The microphone I'm speaking into is taking in analog signals, it's converting them to digital ones, and then it's converting those back to whatever you're listening to my video on, such as your speakers or your headset. There's some example of analog devices, like old CRT televisions and oscilloscopes, classic radios, before they became electronic, just basic AM, FM receivers, uh, set tape recorders and players that includes reel to reel. Some of the early VCRs were analog. Um, Basic telephones were analog, and even some of the first radar systems were purely analog as well. I just described analog versus digital, but let me get into the specifics. So basically, what's the difference between analog and digital? Well, analog is just waves of continuous values. In theory, they could be infinite number of values, such as the values of what sound is. It's just basically air pressure. And we often round down these values a bit so they're a bit more manageable. And lastly, if it's not digital, it's basically analog by definition. Whereas digital means discrete values. Often we talk about it in binary, such as on, off, low, high, true, false, 0, 1, whatever. And this precision and discretion is basically necessary for a lot of electronic devices, such as computers, or at least digital ones. And conversion between analog and digital happens all the time. It's not only possible, but it just happens constantly. Again, analog through the microphone, converted to digital, digital converted to analog through your speakers. And there's so many different ways to handle this in terms of circuits, processes, whatever to implement it. And of course, each implementation has its own pros and cons. Keep in mind, resolution is important, and it often describes the precision and the detail to this conversion. Now let's move back to electricity. we're going to need to talk about the difference between direct and alternating current. I'll go over what current is in a later slide, but for now, keep in mind that a direct current is electric current that is unidirectional. It just moves one direction, and it's think of it as the default and original form of both current and electricity. Keep in mind that even this can vary a little bit because of noise on the line. Um, while it is simple, it is incredibly inefficient for a number of reasons. The first is long distance power transmission. Even more complex to change voltages. When electricity was first developed, um, basically power transformer stations would have to be located every couple of buildings, if not in each building. For small city application, this wasn't too bad, although it was bad, but it would have basically made electrical development in rural areas basically impossible, if only because of the sheer expense. You would have to have power transformer stations every couple 100 feet, maybe even shorter than that. It's also really not good for generating high voltage in situations that you might find in various industries. Regardless of that, in hobby and small electronics, we'll basically just be doing direct current using batteries and adapters and whatnot. Although I will mention alternating current from time to time. The good thing is conversion from DC to AC is really easy and it's commonplace in everything you use on a daily basis. Computers convert AC to various DC voltages. Anything that has a power brick or transformer or power supply most likely does the same thing. And if you've ever plugged a USB cable into a wall adapter, put that wall adapter into your outlet, you're dealing with that all the time. Now let's discuss alternating. Because of the problems with transmitting direct current, another form was finally formalized by Nikola Tesla in 1886. Basically, it alternates the current back and forth, so it's bidirectional, and it's constantly moving the flow in basically sine waves or something similar to sine waves. Um, this alternation is actually measured in hertz, and which is basically just number of cycles per second. While Tesla formalized it, he didn't actually really invent alternating current. It was built on a lot of different concepts. There was work done throughout the 19th century, such as electrical induction by Michael Faraday, which basically made electrical generation possible. AC is easier to transmit over long distances, easier to convert into higher voltage, and it basically brought electricity to everybody. DC to AC conversion is known as inversion, and then AC to DC conversion is known as rectification. Now, I really need to mention that AC from a wall outlet or pretty much any significant source incredibly dangerous. It varies from 110 to 240 volts and 50 to 60 hertz, depending on where you live. Generally, don't want to tap into a wall outlet without an adapter. It can cause electrocution, burns, damage to things, destroy things, or even kill you. So don't just go shoving wires into wall sockets. Before we get into anything else, I really need to talk about units of measurement. Just to keep in mind, mega means millions. Usually it's designated by a capital M. Kilo means thousands, designated by a capital K, but there's plenty of instances where it's a lowercase k. You don't see a prefix, you're usually talking about ones, tens, hundreds place. Milli means 1,000th. So, one thousand, 1,000 millis, and no prefix usually designated with a lowercase m. Micro means 1 millionth. So, 1 million micro, whatever, up to no prefix. It's designated by a lowercase Greek letter mu, but a lot of the times you can use a lowercase u in a pinch. And then we got nano, which is 1 billionth. That's designated by a lowercase n. And then finally pico, which is 1 trillionth, which is designated with a lowercase p. Now we're going to move into volts, current, and resistance. The first thing to show you is the Veer pyramid, which helps you figure out how to convert between the three. A lot of people do that in basic science classes. Now that I've described the Veer pyramid, let me explain how that all works. The V in the pyramid, that stands for volts, which is a unit of measurement for electrical potential difference between 2 points in a conducting wire. You can kind of think of that as a ball on the top of a hill before it actually gets to start to roll. I stands for current, and the reason it's I is because the original term was intensity of current. It's the rate of flow of electrons between 2 points, and is measured in amperes, which is usually shortened to amps and designated with an A. R stands for resistance, which is the total amount of resistance in a circuit against the flow of electricity. It's measured in ohms, which is designated with the Greek symbol omega, although you can sometimes just simplify it, say ohms, or even the lower uppercase u. The elements of electrical flow are all proportional to each other. That means if you know two of them, you can figure out the third. You want to figure out volts, that's current times resistance. If you want to figure out current, that's volts divided by resistance. If you want to figure out resistance, that's volts divided by current. Keep in mind that all the unit of measurements have to be the same. As we talked about on unit measurements, you can't use 100 millivolts and 1 amp and 3 megavolts. You actually have to do the conversion for the numbers to go correctly. Okay, this takes us to Ohm's law, which basically states that electric current through a conductor between 2 points is directly proportional to the voltage across those 2 points. Thanks to the constant of proportionality, if you know volts and current, then you'll be able to figure out the resistance of the circuit. Named after George Ohm, whose name is a unit of measurement for resistance. He wrote a treatise on these properties in 1827, although this work was partially based on other scientists who figured out parts of this earlier. And these concepts were also arrived at independently at about the same time by others. Now, in terms of these three fundamental elements, in terms of voltage, we'll probably be talking volts or millivolts. A lot of that will just be between 0 and 5 volts because we're dealing with hobby electronics. Although if we get into motors, it go up from there. Amps, we'll probably be talking about amps or milliamps. Usually much of the work will be between 0 and 1 amp, maybe even as few as 0 to 500 milliamps. And then ohms, we'll mention in ohms, kiloohms, and maybe even mega ohms. And I think most of the values you'll hear will be between 1 and 1 million ohms, which is 1 mega ohm. Let's first talk about volts. V stands for volts. So just as a reminder, it's a unit of the electrical potential difference between points. Of course, per Ohm's law, volts equal current times resistance. An AC wall outlet probably produces between 110 to 240 volts, depending on your location, at either 50 or 60 hertz. Again, that can be incredibly dangerous if you're not careful. Batteries, we'll be dealing with double A's, triple A's, 9-volt batteries for the most part. Many batteries, they're single cell, so they provide like 1.2, 1.5 volts each. And often the battery type is just the form factor. It's not providing any more or less. Same thing with coin cell batteries. This is often why things don't run on a single battery. You need one, two, three, four, whatever. 9-volt batteries are a little bit different because they have multiple cells, so they'll provide somewhere between 7.2 and 9.6 volts each. And while there's that, why there's that range, we'll explain in a later video. Usually with power sources, we'll be talking about ones that provide either 5 volts or 3.3 volts. And then lastly, USB provides a pretty carefully regulated 5 volts. Okay, so as we previously mentioned, I stands for current. The original term was intensity of current, and it's the measure of flow of electrons between points. Per Ohm's law, current equal volts divided by resistance. Ratings can either be how much the device draws or how much the supply provides. Batteries are actually measured in milliamps years per hour. We'll cover more on batteries in a future video. Um, the Arduino Uno Rev 3, it technically can provide up to 500 milliamps, but keep in mind a lot of the power is used by the device itself, so it's more like 2 to 300 that it can provide to connected components, and there's even further limitations recommendations. The Raspberry Pi 3 Model B, I mean, that's a single board computer, so it actually uses up a lot more power, but it provides a lot more options. Um, So even, up to connected USB devices can actually draw 1.2 amps. Wall chargers really vary. Like there's a lot of variation for large number of reasons I could devote to a video. But they can provide up to like 900 milliamps. And then when you've got newer power delivery options with modern USB-C and quick charging, that can be all the way up to 5 amps. Lastly, we get to R, which stands for resistance and total resistance in a circuit against the flow of electricity. And per Ohm's law, resistance equals volts divided by current. Keep in mind that ideal circuits, such as on a circuit simulator, don't factor in all the sources of resistance. There's sources of resistance where usually it's tiny amounts that don't necessarily matter much, such as in wires and components that aren't resistors. If you do some measurements on a real circuit, you won't get precise numbers and they won't fit nicely into a perfect equation. The idea there is close enough. Then resistors are passive components that we put into a circuit to create intentional resistance, voltage, and current for a number of reasons. All right, let's do some basic example calculations here. Keep in mind this is ideal circuit stuff. Um, we've also converted everything to standard units, volts, amps, ohms without any prefixes. So if we have 5 volts, we have 2 ohms. We're going to know that the circuit has 2.5 amps of current. If we have 2.5 amps of current and we have 2 ohms, we know the voltage is 5 volts. If we have 5 volts and we have 2.5 amps, we know the ohms is 2 ohms. We'll get to in a later video. Now, here's an example using every circuit. You'll notice the power source, you'll notice grounds and the resistor, and it's calculated the numbers already for us. So each one source is 5 volts and it's a voltage source, and one source is 2.5 amps, just to show you how this is calculated differently. Each resistor is 2 ohms. So yeah, we have 5 volts. Um, Divide that by 2 ohms and we get 2.5 amps. We have 2.5 amps and we times that by the 2 ohms, we get 5 volts. Um, we want to figure out the resistance. Yeah, just divide volts by amps and we get to pretty much just that simple. I'll go over how to use every circuit in another video. Now, here's something similar in Halstead Circuit Simulator, which is a completely free program provided you can either use the web browser version or download the JavaScript based version. They have 3 different circuits, actually with different values here, just to remind you. Yeah, the first one, we've got a 1 volt source, we've got 1,000 ohms, and we've got which is producing 1 milliamp. Keep in mind, I had to change to the standard units of measurement here. That's why you see 0.001 amps instead of 1 milliamp. The second example is using 2 volts, but the resistor stays the same. So as you see, we go from 1 to 2 to 5 volts, going from 1 to 2 to 5. So you might want to play around with these numbers. And there's a thing called circuit simulators, which is basically any software-based way to simulate a circuit. Keep in mind if you're brand new, that limits your options a little bit. There's every circuit, which is web-based entirely. It's very friendly to use on a phone. There's a free version, about 15 bucks, United States dollars. Will get you the full one. I think it's very worth it if you want to learn. If you want something that's more free, there's a thing, Halstead Circuit Simulator. It's sometimes just called circuit.js. There's both a web version and a downloadable JavaScript-based version, which means you, I think, make it work just on about any graphical platform. There's some other stuff. There's like Circuit Lab. If you want to get really complicated, there's LT Spice. There's whole videos on that. Microcap, um, Simu, IED. There's a few others. So you may actually want to move into the real world of hobby electronics. Probably not sure where to get started. Probably look around for kits that have a bunch of things in them. There's cheap Arduino compatible kits, like as low as $30. USD. More usually have more components, but you'll need wires because obviously you need some kind of electrical conductor. You'll need resistors, power source, which actually includes a ground, because you've actually got to roll that ball down the hill. Breadboard, technically not required, but trust me, it'll make your life a lot easier unless you want to twist wires together. You'll probably want capacitors, diodes, LEDs, some other stuff. Again, if you buy a kit, they'll really have all the basics in it. Breadboards can come cheap, or you can get better quality ones. Cheap ones may run you less than $10 for a pack of a couple of them, whereas a single good breadboard might be $10 or whatever. If you're just getting into it, just get a couple of cheap ones, and then if you have need for more expensive ones, then that decision later. It'll be really helpful if you have a digital multimeter, because if you want to take actual measurements of volts and current and all that, um, you can get a really cheap one, and honestly, you should always have one on hand just for everyday household use. I've seen them as cheap as $20, but honestly, I would spend more than that. I'd spend, at least 50 or 80, especially on something you might actually want to use in the real world. Um, Power supply modules for breadboards are actually pretty cheap. Um, and you get cheap ones for as many as 4 or 5 for 10, $12. A lot of kits are probably going to come with at least one. They'll usually have a DC barrel jack that to connect to wall adapters or batteries. And most of them have a USB connection. Some may even just have a USB connection. And then you just plug it in. The module handles voltage regulation, uses circuit breakers, etc. You don't have to worry about that. There's examples out there that have you just get a battery connector and just shove wires like that. I don't really like going with that. Although if you do that with the USB cable, the adapter handles a lot of the stuff that the module does, but not a big fan of just plugging a 9-volt battery with two wires into a breadboard. Um, you have Arduinos, Raspberry Pis, whatever, because a lot of these kits may come with something. You could technically use those as a power source because, again, it does everything that a power supply module does. There's issues, limitations, and caveats with that, so be careful. But if you're using it for really simple circuits, like to kind of simulate Ohm's law, you shouldn't have to worry. So, as we come to the conclusion here, keep in mind something like every circuit or Falstad can let you explore all these fundamental concepts without any kind of risk destroying or damaging real world components. If you really just want to get into it in real life, be careful of any dangers of electricity. And obviously, don't just shove wires into AC outlet, just like your parents told you not to shove a fork in there. Although if you use a wall adapter, some kind of AC adapter, that's perfectly fine and safe for your purposes. Um, you'll probably be wanting to deal with 5 volts, 3.3 volts, or whatever. Keep in mind that if you're using a circuit simulator, it won't match the results in real life for a large number of reasons. It'll give you sort of a ballpark answer, and in a lot of cases, if something's close enough, something says 5 volts and you're getting 5.1 or 4.9, probably close enough for most applications. Having trouble with the concepts, just learn one thing at a time. Don't get discouraged by everything or the heavy mathematics and textbooks. I'm personally terrible with math. I let a computer do that for me, although it is nice to know what you're using math for. But yeah, until next time, have a good one.